Okie dokie. Good morning, lads and ladies. Welcome back. I wanted to talk to you a little bit about the MyOpenMath gradebook. Those of you who are trying to track your course grade and there may have noticed some changes lately. Hopefully those changes were soothing in nature, because I found a handful of things in the master course that were set up in a way that is confusing at the very least. Basically, it is the case that the MyOpenMath gradebook by default was set up to measure your grade out of the total completeness for the course, meaning like, even if you got 100% on exam 1, it was showing your exam average as 33.3%, because that's one of the 3 midterm exams that you had completed and you got full credit on it. That was probably pretty scary. And I spent some time talking with the MyOpenMath support staff about things that students can do on their end to change how the gradebook is viewed, and things I can do on my end to change how the gradebook is viewed. Spent a little bit of time tweaking the thing itself, and it is fixed now as far as I know. So if you click on the gradebook in MyOpenMath, you should, from this point on, see your grade exactly as it is right now, not as it is as a total out of the rest of the course, but as it is right at this moment out of the things that we've already done. There's one downside to this, and that is that if I move due dates around at all, things can disappear from the gradebook until that due date goes back by, because the way MyOpenMath works, the setting I had to change was to count only assignments that are past due in the grade calculation. So if I move something forwards so you can work on it more or something like that, then then that's no longer going to be past due. And those of you who've already completed that assignment will see that assignment drop out of your grade calculation. Now, this isn't something that happens a lot, so I don't think it's something that is going to crop up many times through the semester, but I just wanted you to be aware that that's a thing. So yeah, the gradebook should now, when you look at it in MyOpenMath, reflect your grade as it is right now, rather than your grade as it would be if you disappeared from the course right now and didn't do anything else for the rest of the term. And I think that the former is the more reasonable way to have the view set up. If you want anything changed, or if you're having a hard time navigating the gradebook, please do not hesitate to let me know. So yeah, that's all. One other thing I was asked to talk about today, if you're having a hard time finding a place to sit down and attend the Zoom lectures, let me know. My department chair has authorized me to free up some space on campus, a few special rooms where students specifically for this class can sit down and Zoom if they need to. But I need to know from you if you need that, because I don't know how much space to try and reserve. And she's just told me to let you guys know if you're having a hard time finding space to sit down and attend the lecture live on campus. If you're on campus and you want to watch it from there, you have to watch it from there. Of course, that's fine. If you're having a hard time finding a space that feels appropriate for that, let me know, and I can help you find some space. Okay. So this is MAC1105 section 015, which is college algebra. And today is the 15th of February, 2022. What we're going to talk about today is polynomial functions. And I've alluded to these a few times. Oh, you can't see the document, can you? So sorry. Oh. The written work has been graded for most folks. Sorry, yeah, let me talk about that. The written work for most of you is done. If you took the test at a non-standard time, then that hasn't been done yet. So if you took like the makeup test or anything like that, if you had to move the date, or if you took the test physically on campus, like in the DRC or anything like that, then those have not been marked, because I'm still not allowed on campus. The first day I'm allowed to return to campus to click that sort of stuff and teach my in-person classes again is tomorrow due to that whole COVID thing. But if you took the test online with the class last Tuesday, then your grade is finalized. The project I have not started yet. I have some other classes that have grades that need doing. So the project probably going to be a little while. I think the other exams for my other classes I have to grade are going to take up most of my grading time over the next few days. I can try to get your projects graded probably over the weekend, but I wouldn't expect projects to be graded before Monday. So probably Monday. If you're having a hard time viewing the feedback on the written work, I know that I got an email from, maybe it was someone in a different class. I got an email from someone saying that the red wasn't displaying, like when they pull up their work, they don't see the comments. If that's the case, let me know, and I can go in and look at it with you. It's probably a browser thing. What I had to do for that other person was have them download the PDF and then open it in a PDF viewer rather than in Canvas, and then they were able to see it. Okay. Polynomial. We've talked very briefly about what polynomials are when we talked about power functions, because there are a few problems there where they asked you to kind of classify functions as power functions, polynomial, or rational functions. I think the place to begin is just by reminding you the sort of definition that I gave you the other day, which was a fairly intuitive definition. And then I'm going to give you a slightly more rigorous definition, or something involving a little bit more in the way of symbols. Try to convince you that they're the same thing. And then we'll talk about some features that these functions have. So a polynomial of degree n is an expression of the form, and this is the formal definition of the form. I'll call it P of x equals. And what I'm going to write here is the thing that we talked about the other day, but I'm going to write it in some symbols. These are, I'm going to write some constants times some powers of x. And the notation for the constants looks a little bit confusing or maybe a little bit complicated, but it really isn't. So this is going to be an times x to the n, and an here is a constant, plus an minus 1, x to the n minus 1, plus an minus 2, x to the n minus 2, plus, let me go all the way down to a2 x squared plus a1 times x plus a0. And this looks like a big scary expression, but it really isn't. The a's here, an minus 1, an minus 2, these are all just numbers, right? Just constants. The index down here, this subscript, the n minus 1, n minus 2, all the way down to 2, 1, and 0, are just to tell you which power of x that constant is attached to. The one restriction we put on these is that an is not allowed to be 0. Hey, that's strange, Emblem. If you could send me a Canvas message, then we can sort that out. It may be the case that there's a submission in there that I didn't see. Sometimes Canvas does have problems displaying things. So shoot me a Canvas message and we'll take a look at that. So an minus 1, an minus 2, all the way down to a0 are constants. And we require that an is not 0. The reason for that is we've said that this is supposed to be a polynomial of degree n, and degree really just means the largest power of x that shows up. We say also that n is a non-negative integer. So n has to be a whole number, and it cannot be negative. It could be 0. It could be the case that you just have a constant term, but cannot be negative, cannot be a fraction, cannot be a weird decimal. And the way we described this the other day when we were talking about power functions, we said these are power functions that have been added up. right? It's a bunch of constants times powers of x added up. And that each of those power functions has to have a positive power, a positive integer power. So that's the kind of other way you can think about what polynomials are, because this formal definition is just a little bit weird looking. So it's just what you get when you add up a bunch of power functions where the powers are positive integers or non-negative integers. These functions have a lot of really nice properties. Like if you multiply two polynomials, you get another polynomial. If you add two polynomials, you get another polynomial. And for reasons like that, we kind of think of them as like the function version of whole numbers. They're very, very nice. Some terminology. This number an we call the lead coefficient, right? Just like when talking about quadratics. The number a0 is called the constant term. So there's the full formal definition of a polynomial. Once you're comfortable with what all of these words mean, you won't need such cumbersome notation. So let's take a look at a handful of examples and see if we can identify the degree. Well, first identify whether the thing is or is not a polynomial. And if it is a polynomial, identify the degree, the lead coefficient, and the constant. So, classify as polynomial or not. If polynomial, give the degree, lead coefficient, and I'll abbreviate the word coefficient as coef dot. This is just a long word, and constant term. Okay, and I'll throw a few things here. So how about y equals -6x cubed plus 2x minus 3. F of x here could be something like squared minus 10x plus 7. Something like p of x about 32 minus x to the 5. And we'll just do one more. Do I have room to play with something here? I'd like to change just one of these things. Yeah, let me put the 7 in f of x on part b under a square root. Okay. So take a second to get these written down. We're going to talk about whether each one of them is or is not a polynomial. And if it is a polynomial, we're going to talk about the coefficients and the degree. Okay, let's come to this guy in part A. -6x cubed plus 2x minus 3. Is this or is this not a polynomial?
It is.
Yeah, this is a polynomial because when we look at the powers of x that show up, they only show up upstairs and they're always raised to a positive power. So those are the criteria we're looking for. This is a polynomial. What is the degree?
Is it 3?
Yeah, that's exactly right. The degree here is 3 because that's if you look at all the powers of x that show up, 3 is the largest one, right? X cubed. So the degree here is 3. The lead coefficient, let me stack these, is what?
-6?
Yeah, -6, right? The lead coefficient is the number that's attached to the largest power of x. So that whichever term tells you the degree, the number attached to that power of x is the lead coefficient. So here we're looking at a degree 3 polynomial because this is the largest power of x. The coefficient of x cubed, the number that is attached to that, is -6. So that is the lead coefficient here. And the constant term would be -3. Okay. What about the function f of x in part B? Is this or is this not a polynomial?
I don't think so.
I appreciate the concern there. That's good. What is it? So what is it that throws up a red flag about this? What about this feels like it might not be polynomialness?
Because there would be a decimal because 7 can't square that evenly.
That's good, right? Yeah, 7 is not a perfect square, right? And when we see square roots show up in these expressions, it's reasonable to be concerned that the thing may not be a polynomial. I claim that this is a polynomial, that this actually doesn't violate this definition at all. But it is meant to be a little bit tricky. So the things we have to watch out for are the powers of x. Do I have any variables that are being raised to a non-integer or negative power? And the answer there is no, actually. Everything is okay. The powers of x are positive integers, right? This is x to the 1, this is x to the 2. This guy isn't one of the powers of x, he's one of the coefficients, right? This would be a0. And we never said that the coefficients have to be whole numbers. It's nice when they are, sure. But the coefficients can be anything in the world, including weird irrational numbers like the square root of 7. So despite the square root here, this is a polynomial. If there was an x under that square root, it would not be, right? Because then that x would be raised to the power of 1/2, which is certainly not a non-negative integer. So I claim this is a polynomial. Let's see if we can fit it into this definition. In fact, this is a special kind of polynomial. This is a quadratic, right? So all quadratic functions are polynomials. They are all polynomials of degree 2. So every quadratic that we worked with back in that section is a special kind of polynomial. It is a subfamily of polynomials where the degree is 2. The lead coefficient here is 5. And the constant term is the weird one, is the square root of 7. And that's okay. So the a's, the coefficients, they're allowed to be any real number.
I just want to clarify. So the power that's raised can't be negative, or it's not a polynomial, or is it the x that can't be negative?
The powers of x have to be non-negative integers. So the powers of the variable have to be positive whole numbers. So if there was an x being raised to a negative power anywhere in here, that would be a problem. If there was an x being raised to a fraction or decimal power, that would be a problem. If there was an x under this square root, that would be the same as raising that x to the 1/2 power. So that would have been a problem. But since there is no x under here, just the number 7, that's okay. Does that feel okay?
Thank you.
If it still feels weird, that's okay too. We should talk about it more. So don't hesitate to let me know if something feels at all strange. Any other questions or comments on the first couple guys here? Anything that we want to look at more closely? Okay. This fella is a polynomial. Again, the fast way to check is just to ask, are there any powers of x here with non-negative or with negative or non-integer powers? Right? But the only power of x that shows up anywhere here is x to the 5. 5 is a non-negative integer. So we're Gucci. The degree is 5. The lead coefficient, the number attached to that largest power term is -1, right? Negative x to the 5 or minus x to the 5 is the same as -1 times x to the 5. And then the constant term here that's 32. Okay. This last fellow, polynomial or no?
No,
Good. Yeah, this is definitely not a polynomial. What's wrong with this one?
the negative degree.
Yeah, this power of x is not a positive integer power of x. It is a negative integer power of x. So that's no bueno. All right. I know this is not the most exciting thing in the world. I wanted to show you a couple kind of tricky versions of this sort of thing. And so same thing. About these guys. Is the first one a polynomial?
I don't think so.
It definitely doesn't look like that definition, right? So that our definition, write this down. I'm just going to write it shortly. A x to the n, it's 1, x to the n minus 1, down to a x plus a 0.
Wouldn't that just be linear?
Technically, you could classify this as a linear function. Yeah, the graph of this function is a straight line. In fact, it's a horizontal line, right? This is a linear function with slope 0. And that's an interesting hint, because if you look at just the last few terms here, a1x plus a0, that would also be a linear function. In fact, if you look just at the very last term, then that would just be a constant function. This is a polynomial. The degree is 0, and that's tricky. So the constant term and the lead coefficient are the same thing.
thought you said that it couldn't be 0.
AN, the lead coefficient itself, is not allowed to be 0. And that's okay, right? So here we don't have the lead coefficient being 0. The lead coefficient is the number 2. The degree is allowed to be 0. So if we look back over here, AN, the number attached to the largest power of x is not allowed to be 0, but n itself is allowed to be any non-negative integer. And that's why I used non-negative instead of positive. This is one of those kind of funny sticking points. The difference between positive numbers and non-negative numbers, a positive number is a number that's strictly greater than 0. A non-negative number is a number that is greater than or equal to 0. So the degree is allowed to be 0. The lead coefficient is not allowed to be 0. That's the idea. So this is a sneaky one. Constant functions are polynomials. They are polynomials of degree 0. They do fit within that definition. Okay, what about the second fella here, f of x?
I'm gonna say yeah.
So I look under here, and it is 100% true that the thing underneath the radical is a polynomial, right? It's a quadratic, and we just said all quadratics are polynomials. But the problem is that it's under a radical. So I would think of it like this. That whole thing is being raised to the 1/2 power. Now, unfortunately, we can't distribute this power. Powers and addition, subtraction, they really don't like each other. You can't distribute a power over a polynomial. You can't take this and give it to each of these terms here. So I can't say that this is like 3 times the square root of x. I can't say that this is -5x or that this is the square root of 7. It's not that nice. But it is true that because there are variables in here, and this expression is being raised to a non-integer power, that this is not a polynomial. And the way I remember this is if you have variables appearing anywhere under a radical, right? Variables showing up anywhere under a radical, not just like the square root of x, but the square root of any stuff that involves x, that's a deal breaker. That's no longer a polynomial. So the thing underneath here, the thing inside here, would be a polynomial. But when you raise that whole thing to the weird power 1/2, when you take the square root of that whole thing, no longer is it a polynomial. All right, last one. What about g of x?
Even though it's a radical, wouldn't it still be a polynomial? Yeah.
I think there are some terms in there that sound on point. If you think back to what we did with power functions the other day, just very briefly, we talked about these things called rational functions, right? Which is a fraction where the top and bottom are both polynomials. So it's true that x minus 3 is a polynomial. That's a polynomial of degree 1. And it's true that x cubed plus 1 is a polynomial. That's a polynomial of degree 3. But when we divide them, the overall thing, kind of like here, right? The thing inside is a polynomial, but when you put it all under a square root, no more. Even though the top and bottom are both polynomials themselves, the whole thing is not a polynomial because there's no way for me to write, to carry out this division and write this as just something times a power of x plus something times another power of x. This division kind of ruins it. So this is not a polynomial. And kind of like my trick here, if there's variables anywhere under a radical, automatically no dice. The trick here, if there's variables anywhere downstairs in a fraction,
This would work if there weren't any, like x wasn't on the bottom.
That's correct. If the bottom didn't have the x, if I cover this up, or even just like this, if the downstairs was just -3, that would be a polynomial, because I could write that as x cubed over -3 plus 1 over -3, and that would be -1/3 x cubed minus 1/3, which is in this form. So as is, because of the variable downstairs, it's not a polynomial. But if you didn't have any variables downstairs, numbers downstairs are okay, just not variables. So some of these can be a little bit sneaky, and it's not my intent to put you through hell with this stuff. I'm not going to try to catch you out a whole bunch, but I do want to show you these little tricks, because these little tricks can help you save points on exams, right? Just very straightforward true, false, or multiple choice questions. Is this or is this not one of these things? Just remember, if there are any variables under a radical or any variables downstairs in a fraction, automatically not a polynomial. Another way you can think of that, remember when we talked about finding domains? Here's a fun fact about polynomials. The domain of all polynomials is -infinity to infinity. And what this means is if your function has any domain red flags, right? We talked about like red flags. The red flags we had were variables under a radical and variables downstairs in a fraction. If your function has any domain red flags, then it's automatically not a polynomial, because polynomials must have this domain. So this means if you remember the domain red flag material from earlier, you can kind of apply that as a trick. I want to be careful here. Just because a function has the domain all real numbers doesn't mean it's automatically a polynomial. There are lots and lots of functions that have that domain, whether they are or are not polynomials. But every polynomial does have that domain. So if there are any domain red flags, automatically you're not a polynomial, and that can be a quick way to catch things out. Or if you want to remember it separately, variables downstairs, variables under a radical, no dice. Okay. So when it comes to polynomials, there's a handful of things that we really want to understand well. The full story of graphing and working with and solving polynomial equations is actually fairly complicated. It's an active field of mathematics still today. But there are a bunch of things that we can say for sure. And many of those things will get us to a place where we can draw the graph of most polynomials. The two biggest things are factoring and how the factors affect the shape of the graph, and this thing called end behavior, which lets me do a goofy dance for you, which is nice and embarrassing, so that helps us remember stuff. If x minus r is a factor of the polynomial p of x, then p of r equals 0, i.e. x equals r is a root. So this is an important theorem. It says that if you know a factor of a polynomial, then automatically you know a root of that polynomial. And remember, root is just a fancy word for x-intercept. This looks like black on here. So when we go to graph polynomials, we would love to know all of the roots. That's a really nice thing to have. And what this theorem tells you is that if you're looking for roots, the way to do it is by looking for factors. Or if you want to try to factor the polynomial, and that will allow you to find the roots. Conversely, if you know that something is a root, you can deduce that that polynomial must have x minus that number as a factor. So let's see if we can work a quick problem like this. Let's find all the roots of the polynomial p of x equals, let's do x to the 4 minus 9x squared. And this could also have been phrased as find the x-intercepts, right? Root and x-intercept mean the same thing. You'll see both of those. We could have also phrased this as find all the solutions to p of x equals 0, right? Because that's what an x-intercept of a root is. It's a place where the output from that function is 0. That's why it is an x-intercept. So our theorem tells us roots come from factors. If I want to find the roots, I should try to find the factors of this polynomial. So p of x is x to the 4 minus 9x squared. Does anybody see anything I can do to factor this polynomial? Think back about your factoring tricks.
Factor out x squared.
Yeah, very good, right? The first thing we should do when we're trying to factor any sort of expression is look to see if there are any common factors in all the terms. So this is a polynomial with two terms, and we should ask, are there any factors between those two terms which are shared or common? So they call it the GCF, right? If there is a GCF you can pull out, that should be the very first thing you do. And here, this term clearly has an x squared. X to the 4 is x squared times x squared. So if I factor out an x squared, then what will be left is x squared minus 9. Okay, so factoring out the GCF is a great way to get started. If there is anything that you can factor out, any factors that are common to all the terms, by all means do that first. We should look at what's left over. Is there anything we can do with this?
Factor out x. No, we can't.
Yes, there isn't a GCF here anymore, but there is a separate trick. So let me list some factoring tricks. First one is definitely GCF. Right, look for a greatest common factor. If there is a factor that is common, pull out the biggest one you can. Maybe there's more than one, but factor out any common factors. Pull out any common factors. My next favorite factoring trick is called the difference of squares, and that's what we're going to use here. This says that a squared minus b squared, no matter what a and b are, they could be variables, they could be numbers, can always be written as a minus b times a plus b. And the expression here, x squared minus 9, is of that form, right? 9 is 3 squared. So this piece here can be factored as x minus 3 times x plus 3 according to the difference of squares rule. Okay, and this I would consider fully factored. But there is one further step we could go to if you wanted, although it's not necessary, it may help you to see the connection to the theorem. I can write x squared as x minus 0 all squared. It's a true statement. X is x minus 0. Those are the same. So x squared must be the same as x minus 0 squared. And now I have this polynomial p of x written as a product of factors, and none of them can be factored any further. So if I just said factor this thing, I would accept this. This would be fine, right? We're trying to find all the roots, and you could do that from this expression as well. But if you want to see the connection to the theorem, x minus r is a factor, p of r is 0, i.e. r is a root, then writing that as x minus 0 all squared might help illustrate that. So what are my roots here?
X equals 0, x minus 0, and x plus 3.
Let's see. I think the formatting, the language you used there changed a little bit. So 0 is certainly a root. X minus 0 is a factor, but I think you said x equals 0, right? And that would be correct. So 0 is a root. From this factor, I see that 3 is a root. So, right, if x minus r is a factor, then r is a root. So the minus sign is kind of built into the thing. So my roots here x equals 0, x equals 3, and x equals negative 3. That's the idea. In other words, you find the roots by setting each factor equal to 0 on its own. It's that same thing we've been doing with quadratics and that you saw in high school and perhaps even middle school. The roots are the solutions to p of x equals 0. So you can set this equal to 0, and you get that x is equal to 0. You can set this equal to 0, add 3 to both sides, you get x equals 3. So the root that comes from this is x equals 3. And you could set this equal to 0. Subtract 3 from both sides, and you get x equals negative 3. So those roots are 0, 3, and negative 3. And it's just a vocabulary thing. The root is the number, and then these are the factors. Since I'm listing factoring tricks over there on the right, the other one that I would want to include here, of course, is the AC method, which is something we talked about back when we talked about quadratics. And there are a couple others. Something called substitution. And I'll illustrate an example of that. I'll probably pull it out of your homework. But before I do something like that, are there any questions on the factoring or the root finding that we did here? Okay. What does this tell us about the graph? Having found these 3 roots, what could I say for sure about the graph of this function? Maybe the question is too open-ended. We know that it has x-intercepts at -3, 0, and 3. That's what this tells us, that there are x-intercepts at those 3 values. If we take a look at the graph in Desmos, here he is. Change my y-axis a little bit. It looks like this. And those x-intercepts are at -3, 0, and +3. And you notice the graph at 0 here looks different than the graph at 3 and -3. There's a reason for that also. It's because the x equals 0 root came from this factor, And this factor, this whole thing was squared. This is x minus 0 all squared. Well, that's called a multiplicity, and we'll learn more about that in pre-calculus, but we'll be very gentle about it here. So for now, finding the roots. We're very happy just finding the roots. So let me grab slightly more challenging guy, something that'll let us play with substitution a bit from your polynomial. Most this one. Well, we might not do this with any substitution stuff, actually. Oh, it looks like we might not be pushing you guys to do substitution anymore. We used to, but it doesn't look like we're doing it now. Okay. Oh, all right. That's okay then. So we won't do substitution. Let me go back to one of those was a little bit challenging. And then we're going to talk about end behavior. Okay. Yeah, how about this? X cubed plus 12x squared plus 32x. All right. We'll look at the things you need for the other parts of the problem in a moment, but just to get a bit more practice factoring, they said find the x-intercepts for this guy. So what we have to do is remember that x-intercepts means roots, and the way we get those is from factors. So if I look at x cubed plus 12x squared plus 32x, with a mind to factor the thing, what do you see? Oh yes, absolutely. We will talk about end behavior. I have this term, and this term, and they all have an x. So there's a GCF I can pull out. And when I factor out that x, what's left will be x squared plus 12x plus 32. And just like the problem we did a moment ago, this piece is done, but this piece, hopefully I can still factor. So I would go hunting for two numbers that multiply to 32 and add up to 12 using this simplified AC method. So can we think of two numbers that multiply to positive 32 and add up to positive 12?
8 and 4.
Very good. 8 times 4 is 32, and 8 plus 4 is 12. So because the lead coefficient of the quadratic piece here is 1, I don't need to do that thing where you rewrite the middle term and factor by grouping. I can just go straight from that to 8 plus 4, x plus 4 times x plus 8. And then setting p of x to 0. We set each factor equal to 0. And that gives me from the first guy just x equals 0. From the second guy, x is negative 4. And from the third guy, x is negative 8. So those are your x-intercepts. Or if you want them as ordered pairs, that would be 0, 0, negative 4, 0, and negative 8, 0. Okay. So nothing too crazy, probably stuff you've seen in one flavor or another in the past. The other thing that we need in order to get a reasonable graph of a polynomial, to understand what's going on with a polynomial function, is this thing called end behavior. End behavior is what the function looks like for very, very large values of x. So as you plug in a bigger and bigger and bigger positive number for x, is the polynomial getting larger in the positive direction or larger in the negative direction? And the same thing as you go the other way. So we kind of have this thing we call the end behavior dance. It's very goofy. And it can be determined just by looking at the degree and the lead coefficient. Before I get into that, because this in your notes is where we have the factoring stuff, I want to give you one more fact. Because the roots come from the factors, and because each factor has an x in it, when you multiply this out, right, this is going to give you an x to the third. And you notice you have 3 factors here. The maximum number of roots for any polynomial is its degree. So the largest possible number of roots for any polynomial is the degree of that polynomial. So if you have a polynomial of degree 5, it could have at most 5 x-intercepts. And conversely, if you have a polynomial and it has 5 x-intercepts, you know the degree needs to be at least 5. Okay, sorry, just wanted to sneak that in there before we talk about end behavior. Let's go ahead and do the end behavior thing. The graphs of polynomials can be quite complicated if you look near the origin. But if you look very, very far away from the origin, they all have the same basic shape. Every polynomial exhibits one of the following graph shapes when zoomed way out. You could have a polynomial where when you zoom way out, the graph points up on both sides. And it could do all sorts of bizarro stuff inside here. Who knows? But when you zoom way out, the graph points up on both sides, just like x squared. It is possible to have a polynomial which, when you zoom way out, points down on both sides. And again, this thing could do some really bizarro stuff in here. I don't care about what's going on except for the arrows at the end. The other two possibilities are that the graph, when you zoom way out, points down on the left and up on the right. Again, could do any sort of crazy stuff in here. And then the last possibility is that the graph points up on the left and down on the right. Now, if you have the graph of the polynomial and you know how far to zoom out in order to see this, then you can always determine the end behavior just by looking at that. But what we want to do is be able to look at the algebra expression for the polynomial and sort out the end behavior just from how the polynomial looks algebraically. Each one of these end behaviors is determined by the sign of the lead coefficient and the degree. So this end behavior here comes from an even degree and a positive lead coefficient. Up on both sides, think like x squared, right? X squared is a polynomial of degree 2. The lead coefficient is 1, which is positive, and he points up on both sides. And it's true that any polynomial where the degree is 2, 4, 6, 8, any even number with a positive lead coefficient will exhibit that same end behavior. The graph will have arrows pointing up on both sides. If you have a polynomial with even degree and a negative lead coefficient, those will always have arrows that point down on both sides. Right? The end behavior there is negative on both sides. So think like negative x squared or 9 minus x to the 4 or anything like that, where the degree is an even number and the lead coefficient is negative. This guy going down on the left and up on the right is associated with an odd degree and a positive lead coefficient. And this last guy is odd degree and negative lead coefficient. So this is what we call end behavior. There is a special notation for describing it. We're going to talk about that in just a second. But before we do that, I want to show you a quick example how to determine this, and then we'll confirm it by looking at the graph in the graphing calculator. Anybody need more time to draw or write here? The big idea here is that the dominant term, the term with the largest power, the term that tells you the degree, for large values of x is really kind of the only thing that matters. So for very large values of x, something like 7x cubed minus x squared plus 5 really just behaves like 7x cubed. And thus has a graph shape and way out that looks like that. So here, let's take y equals 7x cubed plus 9. B, let's say y equals 8 minus 4x squared. Here, that's 5 x 1. I want to determine the end behavior. So we're just going to draw a little graph with the arrows, right? We'll just draw the graph with the arrows pointing up. That end behavior dance, by the way, is just that, pointing the direction of the arrows. If you sing to yourself about the degree and the lead coefficient as you do this, kind of like the quadratic formula thing, you can embarrass yourself enough to help it stick. There's a very cute XKCD about this. Enjoy that comic. So what's the end behavior for this guy? Is it up on the left, down on the right, up on both sides, down on both sides?
Up on the left and down on the right.
It's close. So the degree here is 3, which is odd. So the arrows will be pointing opposite ways, right? Up on the left, down on the right, or up on the right, down on the left. The lead coefficient is 7, which is positive. So if I have an odd degree and a positive lead coefficient, then my arrows will go down on the left and up on the right. In part B here, my degree is 2, right? The largest power of x is 2, which is even. And my lead coefficient is -4, which is negative. So I have an even degree and a negative lead coefficient. Even degree means the arrows are going to point the same way, either both up or both down. And the negative lead coefficient tells us that they're going to be pointing down on both. This next fellow is an odd degree with a positive lead coefficient. 5, which is odd. The lead coefficient is 3, which is positive. So again, we have an odd degree and a positive lead coefficient will be the same as this guy. Down on the left, up on the right. And then the last fellow here, the degree is 4, even. And the lead coefficient. What is the lead coefficient for this one? This last function.
1.
Yeah, excellent. Remember, if there's nothing written there, that's a 1. Right? X to the 4 is the same as 1 times x to the 4. 1, which is positive. So even means the arrows are going to point the same way. Positive lead coefficient means they're both going to point up. Oh. It is a little bit cumbersome to have to draw this picture every time I want to describe the end behavior for a function. And as much fun as the dance is, it doesn't really go well on paper. So we develop a notation to describe end behavior. And it's a notation that, especially if you're going to take calculus, you will be seeing more and more and more of. We call it the arrow notation or the goes to notation. We can use it for end behavior. We can also use it for other stuff, but we're going to introduce it here with end behavior. I'm going to draw each of these 4 pictures. It's up on both sides here. Behavior. Down on both sides. right. Up on the right. Down. What we're going to do in each of these cases is say as x goes to positive infinity, y goes somewhere. And as x goes to negative infinity, y goes somewhere. Think about this first picture. If I tell you as x goes to negative infinity, y goes, and I'm going to put something after that second arrow, what makes sense to put here? Well, I'm talking about what happens to the graph as x goes to negative infinity. Remember, the x-axis is the horizontal axis, and negative infinity is like really far in this direction. So what we're describing here is the left arrow. When I say as x goes to negative infinity, I'm talking about what this function does for very, very large negative values of x. Since this arrow on the left is pointing up, as x goes further and further and further to the left, the y values go further and further and further up. Right? Remember, the arrow indicates it goes on like that forever. So as x goes to negative infinity, the graph is going way up here. And on your y-axis, way up here is going towards positive infinity. So to describe this arrow, we would say as x goes to negative infinity, y goes to positive infinity. And you could transpose this. You could say y goes to negative or y goes to positive infinity as x goes to negative infinity. But the big idea is this says going left corresponds to going up. Does that make sense?
Kind of.
It's a little bit weird. Just think of on your x-axis, think of negative infinity as a really big number that way. And on your y-axis, think of positive infinity as a really big number that way. And what we're saying is if your feet are glued to the graph, as you walk further and further to the left, letting your x value get closer and closer to this really big negative number, because your feet are glued to the graph and the graph goes up, your y value will be getting closer and closer to this really big number. To describe the arrow on the right, we would say, well, as x goes to positive infinity, as I wander further and further to the right with my feet stuck to this graph, my y values are going up. So as I go really far to the right, that means as x goes to positive infinity, if I'm walking along this graph and letting my x value go off to the right, because this arrow is pointing up, my y values are going to positive infinity. And that would be the goes to or arrow notation for this end behavior. This describes the arrow on the left. This describes the arrow on the right. I'm going to fill in the others here. This guy would say, as x goes to negative infinity, y goes to negative infinity, meaning as we go far to the left, we go down. And as x goes to positive infinity, y goes down. So y goes to negative infinity. So down on the left means as x goes to negative infinity, y goes to negative infinity. Down on the right means as x goes to positive infinity, y goes to negative infinity. This fellow, let's say as x goes to negative infinity, I wander off to the left, my y values are going down. So you say y goes to negative infinity. And as x goes to positive infinity, y goes to positive infinity. And the very last guy here, as we go to the left, the graph goes up. So as x goes to negative infinity, y goes to positive infinity. And as we go to the right, we go down. So as x goes to positive infinity, y goes to negative infinity. This notation is evocative of something called a limit that you will learn about in calculus if you choose to take it. But it is a simplified version that we use just here to talk about how the graph looks for very, very large values of x. Okay. So I promised to take a look at some of these graphs on the calculator, and we can try to contextualize this a little bit. Let me begin with this. Let's do part D. We'll just look at that one, and then we can scoot, because I know you guys are getting short on time here. So first I turn on my calculator, I hit y equals, and I'm going to type this guy in. I type that as x raised to the power of 4. And then I get down out of that power if you're using an 83, remember powers in parentheses, plus 2x raised to the 2, down out of the power, plus 1. Now we see this thing. It looks like a parabola. It's actually not, but it is similar in shape to a parabola. And you can infer pretty reasonably that these guys continue going up and up and up and up. If you wanted to, we could, let's see, increase our y max, something like 500, and set the y scale to something like 10 if you want, and see if this helps us. Yeah. So again, the graph definitely just going up and up and up on both sides. So if I wanted to describe this guy's end behavior, which we got correct, drawing it like this, I would say as x goes to negative infinity, y goes to positive infinity, that's this arrow. And as x goes to positive infinity, y also goes to positive infinity. That's the arrow on the right. Okay. So this is where we're at for time. If you want to talk to me about anything, shoot me a Canvas message. Emberlyn, if you could send me a message about the issue you were having seeing the feedback in Canvas, I would love that. There might be a problem there where I wasn't able to see a file, and if that's the case, we need to get in there and rescore based on that file I'm not seeing. If you have questions about any of the homework poems, of course, come talk to me. We'll do those in office hours, or you can shoot me a picture of your work, and I'd be happy to help you with whatever it is you're stuck on. Take a look at the polynomial stuff. I think that if I'm honest, I would like to spend a little bit more time on this. I don't like rushing this. So probably what we will do on Thursday is play a little bit more with polynomials and also that activity. I wanted to do an activity today, but I didn't have time to prep it. So on Thursday, we will do our third activity. We'll talk a little bit more about polynomials, and I will push the due date for this back a little bit further. So yeah, you don't need to watch me do it. Okay. So if you need to talk about anything, Canvas message, office hours, you know the deal. Next time, we're going to talk a bit more about polynomials, and we'll do our third activity. And if you're having any questions, comments, concerns about the test, anything like that, please don't hesitate to reach out. You can come to office hours, or you can shoot me a Canvas message. All right.
Thank you.
Of course. Take care, guys.